Here's an example of the reverse calculation. You can always look up the Ka of an acid. There's a table in the back of your textbook in Appendix B. And you can calculate the theoretical pH of that acid at any concentration you want. Here, let's calculate the pH of a 0.52 mole per liter methanoic acid solution. Now, because methanoic acid is a carboxylic acid, we need to use Bronston-Lowry theory and create an equilibrium. Because this is an equilibrium, I'm going to need an ice table. If I start off with a 0.52 mole per liter concentration, what will the pH be? Well, the pH is related to the concentration of hydronium at equilibrium. Let's solve for that by defining it as being X. Because there's no other chemicals listed, we're going to assume the concentration of both of the products start off being 0. Then I can fill in the rest of my ice table. Remember, you have to move from one chemical to the other using a mole ratio. Now let's set up our equilibrium expression. And plug in our values in the equilibrium line of our table. The question tells us that this constant is equal to 1.8 times 10 to the minus 4. Now we need to solve for x. I want to try to avoid doing a quadratic formula, but I don't have a perfect square. Let's try the assumption. If I take the lowest initial concentration, 0.52, and divide it by the constant, it is significantly greater than 500. That means the assumption works, and that x will be so small that if I subtract it from 0.52, it won't make a difference. I'll get 0.52. Let's simplify with the math. My numerator becomes x squared, and if I take 0.52 and times by 1.8 times 10 to the minus 4, I get 9.36 times 10 to the minus 5. If I take the square root of both sides, 9.67 times 10 to the minus 3 moles per liter. If I want the pH of this acid, I'll take the negative log of x. Which equals 2.0. Remember that polyprotic acids have multiple hydrogens available for donation, but usually only produce one H+. Polyprotic acids have different Ka values depending on which proton you're donating. Successive donations are weaker, so when calculating hydronium concentrations and pH, only the first proton transfer needs to be considered. The following example proves this. If I have a phosphoric acid, it can donate 2 protons, and when it does, it dissociates with a Ka of the first proton being 7 times 10 to the minus 3, and for the second proton being 6.2 times 10 to the minus 8. Let's calculate the pH of a 3.5 mole per liter solution. We'll start with the first proton donation. We'll use Bronston-Lowry theory. If we have a 3.5 mole per liter solution, and we don't add any products to begin with, I can calculate the hydronium concentration by letting it be X, just like in the last example. The Ka for the first proton is 7 times 10 to the minus 3. Now I need to solve for X. I don't want to do quadratic, but the assumption works. Just barely. If I take 3.5 and divide it by the Ka, it just equals 500. That means I can ignore this minus X here. The top simplifies to X squared, and if I take 3.5 and multiply it by 7 times 10 to the minus 3, I get 0.0245. If I take the square root of this, then X will equal 0.157 moles per liter. That will contribute some of the hydronium that will affect the pH. Now let's look at the second donation. This H2PO4 can donate another H. Let's write an equilibrium showing it. Now, it will have an initial concentration only created by the first donation. In our other ice table, its concentration at equilibrium was defined as X, so it will equal 0.157. None of HPO4 2- is in my system, but I already have an initial concentration of 0.157 mole per liter of hydronium from the first donation. Let's define this concentration here at equilibrium because it starts off as 0 and it will make the math easier. My second donation has a Ka value of 6.2 times 10 to the minus 8. To avoid expanding out and doing quadratic, let's try the assumption. And it works. If I take my lowest concentration, 0.157, and divide it by the constant, it is far greater than 500. That means if I subtract X from 0.157, it won't make a difference. I'll get 0.157. That also means if I add X to 0.157, it won't make a difference. I'll get 0.157. That makes the math very simple. X equals 6.2 times 10 to the minus 8 moles per liter. Now, to get the pH of my acid solution, I need to take all of the hydronium into account in the system. I get 0.157 moles per liter from the first donation, and I get 6.2 times 10 to the minus 8 moles per liter from the second donation. If I add those together and take sig digs into account, the second donation is so tiny I only get 0.157 if I keep 3 sig digs. This proves that only the first donation drastically affects the pH, and you only have to do one ice table calculation for the first H falling off. The pH of my phosphoric acid solution is just going to be the negative log of 0.157, which is 0.81 moles per liter. Now that this is proved, then you only need to take the first donation into account, which is why you were previously told when writing equations involving polyprotic acids to only produce 1H plus or only take 1H off. Now, why does it get harder for acids to donate more than one proton? This is due because of Le Chatelier. Because the first donation produces hydronium ions, it blocks the forward reaction from going due to the common ion effect.